314 Education. Right now, I'm just going to double check we've got our audio levels working just right. I don't want to have there be any weird sort of artifacts going on during our stream together tonight. So I'm just got to grab a little digital pen here. This is not letting me see it yet. That's okay. We expect there to be a slight delay based on the computer taking the time to send the stream out, and from then the stream receiving. I just want to make sure I can hear it and make sure that the sound is all good. But then I won't be watching the feed there. We'll just be engaging like this. If you have any questions for me throughout our time together tonight, feel free to type them into the chat. I will do my best. I have it set up on a window kind of over here in this region, so if you see me kind of turn my head like that, this is me checking the chat window, also checking the health of the stream. But I'm going to try not to do that too much. I want to focus, try to keep it with you guys and focusing on the problems we've got at hand here. Do we have audio yet? I just want to double check, make sure that's working the right way around. All right, it looks pretty good. Cool. Well, so today we are beginning our 8-part series for review for the AP Physics 1 test. Now, the AP Physics 1 test has an in-person option and a digital option. The in-person option I know is available on May the 5th. I'm actually not sure what the date is for the digital one. I probably should have checked that before we started, but I know it's later. It is sometime in June. I want to say June 6th, but don't quote me on that. All I know is if you are taking this digitally, you have a little extra time to prepare. The digital one is going to be a little bit more multiple choice focused. So both tests will have 2 sections, a multiple choice section and an FRQ section, both of which begin, the multiple choice section is 50 multiple choice problems, but the second section is where these two differ. Now, the second section for the in-person is only the FRQs. We'll talk a little bit more once we get there about the different types of FRQs. But they're all going to be your kind of full written out free response type questions. Now, the digital one has the digital one still has multiple choice questions in this FRQ. So you will be taking 25 multiple choice questions. I need to fix something on Twitch real quick. Sorry about that. But so you will be taking the 25 multiple choice sections in the second one, meaning that overall you will have you will be having 75 multiple choice questions as opposed to 50. Now, some people, they prefer this. Some people prefer the online, prefer the open-ended type of problems here. Yeah, sorry, I believe the category is incorrect on the Twitch stream here. I'm going to really quickly fix that manually, if it will let me. So I'm using Restream. Can I change the category? Here we go. Update title and more. So yeah, category, let's change this to just chatting. I think that is probably our best category option here. Yeah, we'll do it like that. There we go. We've been updated. That looks good. All right. Sorry about that confusion, everybody. Cool. So I think we're good to go here. Again, we're beginning this series today. So we've done one test maybe a month ago. Some people may remember, but we're still kind of fleshing things out a little bit. So we are open to feedback. Let me get the chat windows up just so I can see them. There we go. All right, and so this is the set of units that we expect to see on this year's AP test. Now, this is shorter than most years. You may usually remember that there was also, in previous years, we had, where's my cursor? Oh, I'm on the wrong window. Here we go. Oh, this is really not going to work, is it? Let me fix So I'm using a digital draw pad, and it is on the wrong window. I am sorry. At least we're getting these problems out of the way now, right? There we go. So that's all set up. This is still in the right window. I can still read that. That's good. Now I can write over here. Good. So what has been on the test in the past, but will not be on the test this year, was also electrostatics, which would be studying kind of point charges, electric potentials, then Coulomb force and Coulomb charges like that. That's been dropped this year. Kind of following with that was DC circuits, also has been removed this year. Between these two, that's actually a lot of content. So this year we do expect to be a little bit easier, but then that does mean we're going to see more attention on these guys. And then the last unit that we're not seeing is going to be mechanical waves and sound. And so these units have all been stripped out. Now, note for this one, we aren't seeing mechanical waves, but we are going to be working with simple harmonic motion. Now, this is very similar to waves. This sort of sets the groundwork for waves. This is objects moving in a sinusoidal behavior, so they're kind of moving back and forth. These would be objects like a mass on a spring or a pendulum. We'll get to that when we have our session on that topic. So the plan here then is so we have these sessions to deal with here, and I'm gonna clear that little underline there. And so we're gonna have 7 sessions, one going through each and every one of these topics on its own. We're going to go through some multiple choice sample problems, and we'll go through some sample FRQs on the topics, just to kind of see what we've got going on. And then for the 8th one, we're just going to kind of go over everything. We're going to look at all the formulas generally, good ways to remember them, good ways to think about how they interact, and just kind of overviews for the test. And that last one will be on the Tuesday, not on the Thursday, because the test is on a Wednesday. So it wouldn't be very helpful if we had that after the test. So our last session, and I will keep you guys updated as we go, but our last session we expect to see on the day before the test, just for your last minute review needs here. But so for today, we're just going to be started with kinematics. Now, kinematics, we're talking about objects moving in space. And we're talking about the relationships between position, velocity, and acceleration, how we can calculate those things to predict things about objects in motion. So I guess with that, let's get started. So we're going to start by looking at some multiple choice problems here. And so right off the bat, we're given 2 graphs. We're given a graph of object A and object B, and it's a little bit blurry, but we can see this, this axis is our velocity versus time, and that is for both of these graphs. So we are seeing a velocity time for 2 separate objects, and we want to see how they relate to each other. So question 1 asks us, which object is farthest from the origin at t equals 2 seconds? So that's going to be which object has a position further away from 0. Now we can relate position to velocity by using it as the area under the curve. Velocity is the rate of change of position. Any people who've taken calculus will recognize this as an integral. So the area under the curve here is we've got a positive area of 1 times 1. So this is a square of area 1. But then we have a negative square showing up underneath it here. And this has the same area. So for our first object, we travel 1 meter away, but then we travel 1 meter back. So after 2 seconds, we're back at the origin. We have a displacement of 0. Now if we look at object B, we start out slower. By 1 second, we're not as far away, but we're continuously accelerating. We're actually not continuously accelerating. We are increasing our velocity as we go. Our acceleration is increasing at a constant rate, and we're just constantly moving away. So we expect by point 2, we have a positive displacement compared to our displacement, which is 0. We expect B to be further away from the origin at 2 seconds. And then 2, it now asks us about which object moves with constant non-zero acceleration. And so acceleration is going to be the rate of change of velocity with respect to time. And so we see in A, our velocity stays at a constant in the top here, and then drops, and then goes constant again. Excuse me. Oh, encore. There we go. Um, and so we have this, our acceleration is 0 for most of this, except for this one weird spike at 1 second when we change directions. But that is still a 0 acceleration, and we wouldn't describe that as constant non-zero acceleration. Now, B looks pretty good because we're accelerating, but if we think about this, the acceleration is going to be, we can relate this to the slope of our velocity. People who are more calculus-minded can use this as a derivative. Derivative is just a fancy word for slope, but just exact at every little point. And in this case, we can see, oh, we start out with a pretty low slope, but then we try the slope somewhere up here, gets a little bit steeper. So we see our slope is not constant. And so if we were to actually graph this, we would expect our acceleration to be a kind of linear graph, right? So it's increasing at a constant rate, but that does not mean that it itself is a constant. This would be something that has t dependence, because as t grows, this grows larger. That would be our acceleration. So our best option for 2 is neither A nor B. We don't expect either of these to have constant non-zero acceleration. Excuse me. 3 asks us which object is in its initial position at t equals 2 seconds. And so we already discussed this with object A, because object A returns back to its initial position. It has as much area above the curve, or area under the curve in the positive section as it does area under the curve in the negative section. I think my mic is getting a little fuzzy. There we go. I think that fixed it. And then B just takes us to a positive location outside of that. So we expect A to return to its initial position like that. Good. So now we're going to take a look at 4 here. We've got a new graph. A graph above shows velocity versus time for an object moving in a straight line. What time after t0 does the object pass through its initial position? So we're looking for position of this. Position is going to be area under the curve. And so under the curve here, we start out going in the negative direction. We are moving in the negative direction at an increasing velocity in the negative way, and then at a decreasing velocity. So we start to slow down, and at this point, when we cross 0 here, we change directions. That's when our velocity goes from a negative velocity to a positive velocity. We switch moving to the other way. So that means every area after this is now in the opposite direction. And so in some region, once we cover enough area, we will overcome the negative area that we had at the beginning, and that means we've passed through our initial position. So we need to find the area of this negative little red triangle we've got down here. So area for a triangle is 1/2 base times height. The base is 1 second, and the height is -1. Although I guess the negative doesn't really matter too much, as long as we just remember that this is in the negative direction. So we have 1/2 times 1 times -1, but the magnitude of -1 is just 1. So that's going to give us 1/2, an area of 1/2. So we've traveled 1/2 meter in this negative region. So we want to find out, when do we reach 1/2 meter in the positive direction? And so that's going to be when we want the length. This goes after here. So mathematically, we can look at that as finding the base of this triangle. Considering we want the area to be 1/2, so the base is going to be area times 2 divided by h. And our h goes from 0 to 2. So we can, okay, so let's find the area of this triangle to begin with here. Yeah, that's actually probably a better approach than this guy. Yeah, so we can do 1/2 base times height again, but this time that is going to be Our base is 1 again, but our height is now 2. So this gives us an area of 1. So we know we've gone past our origin at 2 seconds. We know it's not at 1 second because 1 second we've turned around. The mic is still buzzing a little bit. There we go. That's a little better. So we expect this to then be between 1 and 2. If we had to calculate this exactly, the approach we had before was a better idea with solving for b initially. But the fact that we can do this generally, we're just looking for something between 1 and 2. That's general enough for us to be able to narrow it down to that option here. Cool. So number 5, we now have a body moving in the positive x direction. It passes the origin at time t equals 0. Between t equals 0 and t equals 1, the body has a constant speed of 24 meters per second. At 1 second, the body then gets a constant acceleration of 6 meters per second squared in the negative x direction. And we would like to find the position of this body at 11 seconds. So the best option for this is our big boy kinematic here. This is the one with all of the terms here. This relates acceleration to time, an initial velocity, and any offset in position. Now, what we can do to make this a little bit easier here, we're asked to find the position of the body at 11 seconds. However, our acceleration doesn't kick in till after 1 second. That's from this line here. At t equals 1 second, the body is then given the constant acceleration. So what we can do is we can actually offset our time scale by 1 second. We'll start measuring at 1 second, and then as our t gets up to 10 seconds, that would then be the equivalent of 11 seconds in this original reference frame. So then what we need to do to adjust for that is we need to add as an initial position the distance we traveled in that first second. However, that's pretty easy to calculate because we traveled at a constant speed, 24 meters per second, for 1 second. So that means we traveled 24 meters. So we expect after t equals 1 second to have an acceleration of -6. We'll still write this generally with our t's here. So that's going to be times our t squared. We have the initial velocity still of 24 meters per second times t. And then we'll add a little 24 to say, oh, we've traveled 24 meters since this acceleration started. And so now we want to find, instead of x at 11, we want to find the x at 10 seconds because we did that offset of 1 second. And so that's going to give us, well, let's actually do this like 1/2 times -6 is -3 times t squared. T is 10. So 10 squared is 100. 24 times 10 is, I guess we'll write this out as 24 times 10, but that is 240. And 24 is just a constant. This has no dependence on t. So we'll start simplifying a bit here. We've got -300 plus 240 plus 24, which we can think of as, we've got 300 minus 200, oh, sorry, plus 264. And so we expect this to then be a negative value because 264 is less than 300. And the difference between these two is 36. So we expect this to be a -36, which is our option C. So far looks good. We have no questions in the chat, so we're just going to assume you guys all understand everything, and we're just going to keep on trucking here. Number 6, we're looking at, we've got a diver initially moving horizontally off the edge of a cliff. He's traveling with some speed v off the edge of a vertical cliff and lands in water a distance d from the base of the cliff. How far from the base of the cliff would the diver have landed if the diver initially had been moving with speed 2v? So if he doubles his velocity. I'm gonna see. Let's actually. I kind of ran out of space on the bottom here, so we'll do this one up in this corner here. And so we can imagine. So he's got some water that he's going into. Let's assume there isn't that little rocky drop off that I accidentally drew. And we've got our little diver here. And so he's running horizontally. Now that's important. He's not jumping up at an angle. There's going to be no initial velocity in the y direction. And so we jump horizontally, and then we just kind of fall, and we land some distance d from the ledge. Oops, that's a d. Now, we can find out what happens when we change this initial velocity by measuring our two parameters. We have our motion in the x direction, and we have our motion in the y direction. And so the y direction is going to determine the time it takes for us to reach the ground. This is going to be 1/2 gt squared. Now bear in mind this is going to be, g will be a negative number because this is going to be like a negative 9.8 pulling us downwards. Plus any initial upwards velocity, but we don't have any initial velocity because we're traveling horizontally. So there's no velocity in the y. Then we just have the offset of the height that we're starting at. We're assuming this cliff has the same height h here. Do they mention the height of the cliff? I guess they don't, but if it's the same cliff, then we assume h is constant. And so we see none of this depends on the velocity. The v doesn't show up at all in this equation for y. And so this would be what we would solve to find out the time we are in the air. And so we could take this and rearrange it for t, but basically all we need to know here is that t is going to be constant. T is going to be the same as it would be if we are traveling at 2v. And now what changes is because our x position we're assuming no acceleration in the x because we are assuming no air resistance, right? It doesn't mention it, but we will assume no air resistance because otherwise none of these options would be correct. And so we increase our x motion is just going to be our velocity in the x direction times time. And our velocity in the x direction is all of our velocity because we're moving horizontally before we begin. So our x direction just scales directly with time and velocity. Time stays constant for both cases because our y equation doesn't change, but the velocity doubles. So therefore we expect our distance to double. And so that's going to give us the option of 2d is our best choice here because we will then travel twice as far. Oh, that kind of moved upwards there on me. I wanted to keep that down like that. There we go. We move to a distance of 2d like that. And so that would just be he's traveling further. Yeah, you guys see what's going on there. Cool. Next we are taking a look at a set of graphs here. We see a projectile is fired with initial velocity v0 at some angle theta naught, with the angle theta naught with the horizontal. And it follows the trajectory shown above. Okay, yeah, and I think we checked this one. There wasn't a graph with this. These questions have been pulled from samples of old AP questions, but sometimes the copying gets a little bit muddled sometimes. But that's okay. We can assume that means we have some initial velocity v0, and then if this is the ground, this would be theta naught. And so we would expect to be traveling in a sort of inverted parabola here. That kind of arcing motion, very similar to what we have down here actually in questions 8 and 9. And so, sorry, just double checking the health of the stream there. And so we're asked to find which pairs of graphs best represent the vertical components of the velocity and the acceleration. And so I don't know if you guys can read these here, but this is the velocities are on the left and the accelerations are on the right, and both are functions of t. And so we are looking for the vertical velocity. We expect to start out positive because that has an initial upwards component. And then it starts to slow down. So we expect this upwards component to get smaller and smaller until it reaches 0 here. And then it gets negative. And it starts getting increasingly negative as we start speeding up downwards. Another way we can think about this is potential energy getting converted back into kinetic energy. But so we expect a velocity behavior of starting positive, reaching zero, and going negative if this were the axis. And so that looks like the option for A, B, and D. So we can rule out C right away. Now our other component we need to have is our acceleration. Now our acceleration, rate of change of our velocity, is going to be a constant. It's going to be a negative constant, and if we want to get specific about it, it would be the magnitude of the slope of this. So if we were to measure the slope, how far this goes down, in the case of gravity, we would expect that to actually be negative 9.8. And so the best option there appears to be D. All the other ones have these kind of like the diagonal accelerations. That implies a changing acceleration, which is not what we expect to happen. Cool. So let's move on to 8 and 9 here. We've got another ball kind of traveling through this projectile trajectory again. Air friction is negligible. That's always nice. We know Q is the highest point here, and P and R are the same height above the ground. So how do the speeds of the ball at the 3 points compare? So we expect this. So when we say speed, that is going to be the magnitude of our velocity, and our velocity has multiple directions here, right? So if we think about we're traveling in this direction at this point P, we're really traveling some component horizontally and some component vertically. Oh, let's draw that a little clearer. There we go. Same with point R here. Point R, we also expect to have, in this case now, it would have a downwards component and still have the same rightwards x component. And so we then see at Q, when we're at our maximum height, our velocity is just in the x direction. There's no up or down because at max height, that is when our vertical velocity reaches zero. On our previous graph, that would be something like at this point here. This was V and T. So this tells us that our point Q is going to be our lowest velocity, because this is just going to equal the leg of each of these previous triangles. They both have this same component, but their magnitude is the hypotenuse, and a hypotenuse is always larger than the leg in a right triangle. And these are right triangles because x and y are perpendicular. And so we then have, so we have our object moving to the right. So we know Q is the least here. So that means we can rule out A and B right away. So next we just need to see how P and R compare to each other. And so they both have equal horizontal velocity, and they will actually have equal vertical components too, because they're at the same height. An easy way to check this would be conservation of energy. But we can also think about this because we can't use conservation of energy in kinematics. Well, technically you can. There's no rules about that on the actual AP test. But for today, we're going to try to stick to kinematic methods. We can think about this as they've traced out the same distance from this maximum and are accelerating at the same rate. So this has the upwards velocity being accelerated for this distance d, or being decelerated. So I suppose we would say our acceleration is going in this way. And then in this case, we see we've traveled the same distance d, because these two are at the same height above the ground, but we are traveling from a speed of 0 to a speed equivalent to accelerating for that same distance. If distances are the same, accelerations are the same, we expect their final velocities to be the same. Therefore, D is our best option here. This puts the velocity of P and R equal to each other. They have the same x components, the same y components, same angles, therefore it's the same triangle. Let's see, which of the following diagrams best shows the acceleration of the ball at point P? Now, acceleration is going to be, we can think of this as the direction of the force that's acting on this. It's the direction we're changing. But we can think our velocity went from like an upwards kind of pointing diagonal to a horizontal to a lower one. So we're changing our direction by pointing vertically downwards. That's also the direction gravity is pointing, if that's an easier way to remember it. And so D is going to be our best option here also. Notice that we're not traveling in that direction at all in Q. We're traveling entirely in the horizontal direction, but we're still accelerating down that way because if we add on some time, we see our direction has been angled towards that more. Good. So let's take a look at this last one here on this page. We've got the graph above represents position x versus time t for an object being acted on by a constant force. Constant force implies a constant acceleration that is due to F equals ma. And we can rearrange this to say acceleration is force over mass. Force is constant, mass is constant, therefore acceleration is constant. The average speed during the interval between 1 second and 2 seconds is most nearly, so the average speed we can think of is distance over time. And so our distance, we go from 2 meters here to, we're at 2 seconds, we go to 8 meters here. So we travel from 2 to 8 is 6 meters, and we go from 2 seconds to 1 second, that's a gap of 1 second. So we are traveling most nearly 6 meters per second. Now we use this approximation because if we look, this is actually kind of curved here. And so it's going to be a little bit slower in the beginning and a little bit faster in the end, but not by a lot. It looks fairly linear just by eyeballing it here. But our best answer here is still D. Cool. And so I believe we've still got a couple more multiple choices. Again, I've curated these problems, but they are a little bit out of order just because we're trying to get them together based on the types of topics here. So we are now jumping to 42 and 43. And so I actually haven't seen these ones before, but I haven't solved these ones before. I did look through these. But we can tackle these as we go. This is good to learn about approaches here. So the following two questions refer to the following information. An ideal elastic rubber ball is dropped from a height of about 2 meters, hits the floor, and rebounds to its original height. And so we want to see which of the following graphs best represents the distance above the floor versus time for above. So we've got a ball, it's falling down, hits the floor, has like a little impact, and then goes kind of back up, right? So that looks like C, right? C gives us our best option here. A looks kind of close, but A starts at the bottom, and we think our ball is starting at a height of 2 meters when we drop it. So A we can rule out. D we can rule out because we don't expect the distance to be changing at a constant like this. That would assume a constant velocity, and that would assume no acceleration. But if it's dropping and falling, we expect it to be accelerating due to gravity. And then B we can rule out because this goes negative. So that would imply we're going through the floor and then bouncing back upwards. And that's not going to be the case either. So C is our best choice here. Which of the following graphs would best represent acceleration versus time for the bouncing ball? Now, acceleration we expect to be constant during its falling time. So we can rule out pretty much all of these but B. So B is going to be our best option here because we have this negative acceleration. This is due to gravity. This is the time when we're falling. Then when we hit the floor, we can think of this as an impulse if you like. But again, we don't need to deal with this too much because that would be, we'll save that more for the momentum unit, which will be next week, I believe. Maybe 2 weeks. I think that's the 4th unit. 2 weeks from now, yes. And so, but we see we have this spike in upwards acceleration. That's going to be this bounce, starting to accelerate our ball upwards. But as soon as it gets clear, right about here, like, you know, once it's free of its compression and then bounces upwards and it's moving upwards, we get to this point in our graph here where we're at a negative 9.8 again. The only acceleration is due to gravity. But now we have that upwards velocity, so it has some velocity to kind of sink into a bit there. So B is our best choice for that one. 44 through 46, we've got the following two questions refer to the following information. They said with 3 questions below. It's okay. At T0, two cars moving along a highway are side by side. As they pass, a third car stopped on the side of the road. At this moment, the driver of the first car steps on the brakes while the driver of the stopped car begins to accelerate. Okay, so I see. They all pass each other, uh, and this shows their positions for each of the next 5 seconds. So we can see this guy is traveling faster, and then he kind of starts to slow down. These time stamps are getting closer. Car 2 is just moving at a constant. He's moving, it looks like 10 meters per second if the gaps are 1 second apart. And then this guy starts out slow. These gaps start closer and closer together, but they get further apart as he picks up some speed. During which time interval would cars 2 and 3 be moving at the same average speed? So that's going to be which time interval do they have the same gaps between their times here. So we're comparing 2 and 3. So the gap between T1 and T0 and T1 doesn't look very good, so we can rule that out. T1 and T2 looks kind of close. That's still less than 10 meters. We know this is traveling 10 meters per second. This is a little less. T2 and T3 looks pretty good though here, because this is, what, if this is about 8 meters, this is about 18 meters. We're spanning about 10 meters in that time span, and so is car 2. Now car 2 is further away from us because it's been accelerating, or sorry, it's had the higher velocity for longer. We're the ones that are accelerating in car 3. But 2 to 3 is going to be the region that we are moving at the same velocity. Same average speed, I suppose, if they want to be picky about directions, which I suppose we should be. Good. Which of the 3 cars had the greatest average speed during these 5 seconds? Okay, so greatest average speed, presumably. So if we can treat this as the time stamps are all the same, right? So they correspond to the same kind of time interval, and so our speed, I guess our average speed, what do we write this as, v bar, would be our distance we traveled over time. And so after 5 seconds, in this 5-second interval, our first car made it 40 meters, so it was traveling, car 1 had 40 meters over 5 seconds, so that's, what, 8 meters per second? 40 divided by 5 is 8, yes. Car 2 had, I probably should have started writing this further up now, but that's okay. Car 2 traveled 50 meters in 5 seconds. That is going to average 10 meters per second. And car 3 had also traveled 50 meters in 5 seconds, giving us again an average velocity of 10 meters per second. So car 2 and 3 had the same average speed. That's going to be option A. If car 3 continues to constantly accelerate at the same rate, what will its position be at the end of 6 seconds? Okay, so we want to see how much we are increasing our acceleration by. So we've got to jump from about 10 at T2 to T3, and then we go, that looks like, if this is like 2, 10, and another 2, it goes up to like 14, so we've increased by 4. And then that would be, if that were to follow through, this would be another 4. So that gives us 8 plus 10. Yeah, so that looks like we're increasing by a rate of 4 meters per second every second. So 4 meters per second squared. And so if we're traveling at, this appears to be 18 meters per second, if we add 4 to it, that means we're going to travel 22 meters per second by the next second, and we'll travel another 22 meters. That puts us at 72 meters away by time t6. And that comes from 50 plus this 22, where we'll be out over here, out at t6. This will be at 72. You know, we can think of 70 as being right there. Cool. Any questions so far? Nope, we look pretty good here. Oh, my window is a little bit screwy though. Can we adjust this window a little? There, that's better. That's been like that the whole time, hasn't it? Did I overlook anything? Okay. Well, we'll just keep going. Okay. Alrighty. I believe this is the last set of multiple choice questions we have for now, and then we're going to take a look at FRQs after this. So we've got a graph representing the relationship between distance and time for an object. You know, distance on our y-axis, time on our x-axis. There's moving along a straight line. What is the instantaneous speed of the object at t equals 5 seconds? So that's going to be the slope at 5 seconds. And that's, let's change colors here because we can't really see that, can we? So that's going to be at this time right here. It looks pretty close to, so before we're kind of traveling from, let's see, that's half a second, we go half a meter. So that's about 1 meter per second. We're starting to slow down a little bit on this end though. See how we're not hitting the corner anymore? So we expect it to be a little bit less than 1 meter per second. That puts our best option as B, 0.8 meters per second. We could do this as a wider average from this to this, but we were able to get it with a short average and then looking at our options. This is one of the advantages of multiple choice too, is you can see the answers before you have to do all the excess work. Between what times did the object have non-zero acceleration? So this would be at what time does our object start to change its velocity? So we can see at this point our velocity is looking pretty constant. We kind of start to change actually around 5 seconds. And so this is non-zero acceleration, but it's actually a negative, which counts for non-zero, but it's a deceleration because our slope is getting less steep. It's decreasing. And so that's going to be in this region from 5 seconds to 8 seconds. Just because C is not a good answer, we do expect this object to start decelerating. B is not a good answer, and A is not a good answer. And we already estimated that it was in this region-ish here is when we start to decelerate. So this is going from here to here. That's, yeah, we see this is starting to change its slope. Good. So next we're shown if a ball is thrown directly upwards with twice the initial speed of another, how much higher will it be at its apex? So this is going to relate to our y kinematic here. Our y is a function of t, is going to be, we have 1/2 gt squared, don't forget we're going to make this g a negative value, plus a v initial times time. We want to know the height that it gets to. So let's see, what would be, yeah, so we can find the okay, this might be a slightly roundabout way of doing this, but that's okay. Actually, you know, yeah, this is a roundabout way of doing this. Let's do this with this relationship here. So this is our other kinematic we have. Well, there's a few kinematics we have. That's an A. So our acceleration is acceleration due to gravity. That's going to be g, negative 9.8. And so we're looking for our v initial is going to be the speed that we launch at. V final is going to be the velocity at the apex, which we know, due to the definition of it being the apex, the maximum height point, this is going to be 0. So we want to see d as a function of v initial. So let's rearrange this for d. So we'll minus vi squared, and that's going to equal 2ad. And then we'll divide by 2a. And so we get d is equal to negative vi squared over 2a. And now a is a negative number, so this negative will cancel out. but it's just going to be a constant. We want to see this vi is the behavior. So we expect d to increase as v gets squared. So as if v goes to 2v, so let's look for the distance for 2vi. As that gets squared, acceleration stays the same. We get a 4 up here now. And so we have 4 times our original answer, which was negative vi squared over 2a. Technically, the negative drops out again because of that a. This ends up being 4 times our distance, right? We can write this as 4d. And so that's going to be option C is our best option here. Cool, cool. Any questions on that? Nope. Looks pretty good so far. A lot of viewers, that's okay. We've got next we're looking at toy cars starting from rest and moving uniformly, accelerating uniformly across the floor. And the time and distance are given on the bottom. So this is like that car problem we saw earlier. What was the acceleration of the cart during the... Oh, it's a cart now. Stay consistent, come on. So what was the acceleration of the cart during the first 0.4 seconds? So we can use this as... so let's look at our changes in velocity. So our initial velocity, we go from 0 to 6 meters in 0.1 seconds. So let's say, we'll call this like V1. And that's going to be 6 centimeters per 0.1 seconds, which is, if we multiply it by 10, that's 60 centimeters per second. Although they want this in meters per second, so we'll write this as 0.6 meters per second. Now let's take a look at another gap here. Let's go from 6 to 24. And so 24 minus 6 is the distance we traveled, which is 18. And so we'll call this V2. We travel 18 centimeters in, again, 0.1 seconds. In 0.2 seconds minus 0.1 seconds, which is 0.1. And so that gives us a velocity of 1.8 meters per second. So we see our velocity increased by 1.2 meters per second. Oh, but we have... That's not an option. That's 12 is our closest option. Did I drop a decimal place somewhere? Let's see. So that's 6 centimeters. That's 0.06 meters. So we can change that. So dividing by 0.1 is the same as multiplying by 10. That's still 0.6 meters. 18 centimeters is 0.18 or 1.8 meters. Sorry, then it's 0.18 meters multiplied by 10 gives us 1.8. I mean, 12 is our best option, but 12 does not look correct. I think I've dropped a decimal place somewhere here. I guess let's check the next gap just to verify. If we get the same gap, then I'm not sure where I dropped the 10 space. So let's do this in meters now. So we travel 54 centimeters minus 24. That is 30 centimeters or 0.3 meters. And this is also, again, in 1 second. So we multiply this by 3. That is, we're traveling at 3 meters per second. Yeah, no, I still get the same answer consistently here. There's been I don't think that I'm screwing this up. I think that they might just have messed their answer up. This is meant to be 1.2. I'll double check that. We can verify that on the next time here. But Yeah, because this then gives us a gap from 18 to 3 is, again, 1.2. We're consistently hitting 1.2 meters per second squared. That looks like our best option. I mean, pretty much all these other ones we can just rule right out because it's not going to be 25, not going to be 9.8. Yeah, that's disappointing. What was the instantaneous velocity of the cart at 96 centimeters from the start? So if we have, oh, this is not gonna play nice now, is it? Well, so we can basically add 1.2 again, right? Because we're accelerating constantly, so that ends up being 4.2, which is not an option. But I guess their acceleration wasn't the same either, so that's unfortunate. So it looks like our best option is 4.8 meters per second. Because yeah, okay, so yeah, because this would be an average uh, across the entire length would be the average of 4.2. So at the end, we expect that to actually be on the higher end, which would be 4.8. 60 is right out, everything else is below it. So B is our best option here. Okay, yeah, a little bit strange towards the end there, but that's okay. So just double checking, doesn't look like anyone has any questions on the board, so we're just going to keep on moving, and now we're going to move to the FRQ section. So these are the free response questions, and this is, you basically want to try grab as many points as you can. There's a lot of partial credit available for these types of problems. You want to be writing out all your work, and we do want to try to get the correct answer. But the correct answer is not all of the points. In fact, it's actually a minority of the points. Most of the points you will get are found during the process you take to solve this problem. So taking a look at this case here, we've got a guy kicking a ball. Yeah, so we've got a ball with a known mass of 0.5 kilograms. It's initially at rest. It's kicked directly towards a fence from a point 32 meters away. The velocity of the ball as it leaves the kicker's foot is 20 meters per second at an angle of 37 degrees above the horizontal. Top of the fence is 2.5 meters high. Ball hits nothing while it's in the air, and air resistance is negligible. So we need to determine the time it takes for the ball to reach the plane of the fence. So that's just going to be, we'll use our kinematic. That is this relation. And so our full version, which we can write out, is our acceleration in the x direction, 1/2 at squared. So let's put a little label, make sure we know that's in the x direction. Plus our initial velocity in the x direction. We'll come back to that in a second here. Times t, plus any initial x offset, excuse me. Now for these cases, we don't expect there to be any acceleration in the x direction. That's because we said air resistance is negligible. So this whole term drops to 0. And then we'll start measuring at this distance here. So that means our x naught is also going to go to 0. So we expect this to be traveling through the air at a constant velocity, and that's going to be the initial x velocity that was given to us. And so we can find this x velocity from our initial one. We know our initial velocity has a magnitude of 20 meters per second, and that is 37 degrees above the horizontal. So in the x direction, we expect there to be an offset of 37 degrees. And then there's the y component, which we'll also want to know. So we can write this as Vx on the x-axis, Vy on the y-axis. We can relate them to this angle here using our trig identities, or our trig relations. So x is adjacent to this angle, so that means the cosine relationship, cosine of 37, will give us our adjacent over hypotenuse. That's the ka in SOHCAHTOA. So our adjacent side is Vx, and our hypotenuse is 20 meters per second. And so to get Vx on its own, we'll just multiply both sides by 20. So we get Vx is equal to 20 times the cosine of 37. Now, in this case, they provided us with our values for cosines, sines, and tangents. I think this is just kind of from it being an older test. This was sampled from 1994. But these days you're allowed to use a calculator, so they probably won't be providing those like that. You can just type in your trig relations directly. So that's just going to be 0.8. So 0.8 of 20, 4/5. 20 divided by 5 is 4, so that's going to be 16. 16 meters per second in the x direction. And I guess while we're at it, let's get our y. And so our y is going to be the sine relation here. We have sine of 37 is equal to our vy over 20. And so then, like we did here, we'll multiply both sides by 20 to get it on its own. So this is going to be 20 times the sine of 37. And 0.6 is 3/5. So as we had 4/5 was 16, 3/5 would be 12. So we expect to have an initial upwards velocity of 12 meters per second and an initial horizontal velocity of 16 meters per second. So let's bring this back down to our original equation here. Oh, that's caught in the offset again. That's unfortunate. In fact, I can fix that on the fly here. Sorry, I didn't realize my top offset was so high. I want to keep it fairly low, just because, or reasonably high, because I want to make sure that you guys are seeing as much of the frame as you can without it taking up too much space. Oh, now the thing's in the way. We'll put that over there. There we go. Okay, just rearranging the stream a little bit to get a little bit more visual space, visual real estate, let's call it. Yeah, and so we want to find the time at which we travel an x distance of 32 meters, because that's when we reach the plane of the fence. And so that's going to be taking this relationship, x equals vx times t, and rearranging it for t, which just gives us t is equal to vx over x. Now in our case, that is 16 meters per second over 32 meters. Meters divided with meters. Oh, that's... something's wrong here. Yep, that is... I got that the wrong way up. So that's how we can double check, is we check our units, and if our units don't line up, we know we've made a mistake. And so I noticed that my units were 1/seconds, which is not right because we expect our units to be seconds for time. And I got that the wrong way around. T is going to be x over vx, not the other way up. There we go, my mistake. Good thing we caught that. Our x distance is 32 meters, and our meters per second is 16 meters per second. So we have meters over meters, meters cancel, and then we have 1/1/seconds, which is just seconds, units of seconds, units look good. 32 divided by 16 is just 2. So we expect to reach the plane of the fence in 2 seconds. I guess we'll put a little label here, right? We'll say that's 2 seconds. Will the ball hit the fence? If so, how far below the top of the fence will it hit? If not, how far above the top of the fence will it pass? So we know this magic time now. What we can do is we can take this to our y relation. We can look at as our height is going to change with respect to time, where we expect our height to be at this 2-second mark. And so we expect our acceleration to be negative gt squared, and we're going to plug in the negative 9.8 as g, so this stays positive, but it will be a negative term. Plus, we do have an initial y velocity. That was this 12 meters per second that we calculated before. And then we do not have an offset. So we would have some y offset term here, but that goes to 0. And so we want to find the height at this time, which is what this is already rearranged for. So all we want to do here is just plug in our values. So we have 1/2 times, we'll use a negative 9.8. Technically, they might be looking for 10 if this was like a non-calculator, because that's going to make it a little easier, but I'm not too worried about it. T squared is 2 squared. We're plugging in for when t equals 2. So 2 squared is 4 plus our Vy, which is 12 meters per second, times our time, which is 2. So we've got 24 here. And then we have 1/2 times 4 is 2 times negative 9.8. 2 times negative 9.8 is 19.6. So we've got negative 19.6. That gives us a height of 24 minus 19.6, which is 4.4. We are 4.4 meters above the ground at this time here, which is going to be somewhere up here because the fence is only 2.5 meters high. So we do expect to pass over the fence. It will pass the fence. I don't know if there's like a shorthand. And to find out how much it passes by, we'll subtract 2.5 from this. So 4.4 minus 2.5 is, let's see, well, 4 minus 2.5 is 1.5, and then add 0.4 gives us 1.9. So we'll say this passes by 1.9 meters. We go 1.9 meters over. On the axes below, okay, so I didn't copy the axes, but we'll just draw some axes. Sketch the horizontal and vertical components of the velocity as functions of time until the ball reaches the plane of the fence. So I believe that the axes were going to be something like this. We'll write this as Vx, that's our horizontal component of our velocity with respect to time, and our Vy, this is our vertical component of our velocity with respect to time. Our horizontal component we expect to stay constant. This is going to be at 16 meters per second until we reach the fence. So this is just going to look like that. Now our vertical component's a little bit different because we start out at 12 meters per second, but we kind of change directions and start moving down. And let's see, at what point do we... So we will pass through 0. If we wanted to be picky about it, we could find out the time that we would pass there. We go by negative 9.8 every second. So at 2 seconds, we're traveling at negative 19.6 meters per second. So we know we've surpassed 12, or sorry, we've changed our initial velocity by negative 19.6 meters per second. We aren't traveling at 19.6 meters per second, but we are still traveling negative, and that's going to be at some point between 1 and 2 seconds. So we'll draw this as a negative constant that crosses over some point. If we want to be really picky about it, we could label these points where we expect them to be, but this just asked for a sketch. So this is going to be all that we need to do for this type of a problem. And in this case, we might as well just leave it like that, because if we make a calculation error, then we would lose those points that we would have otherwise gotten for leaving it blank. So it's in our best interest to leave this problem as is. Just double checking, seeing if anyone has any questions. Again, we're looking pretty clear, so I'm just going to go ahead and keep on trucking. Alrighty, what have we got here? Okay, so we've got a ball of mass m is released from rest at a distance h above a frictionless plane. And the frictionless plane is inclined at an angle of 45 degrees. That's what we've got kind of coming down here. We drop, and then the ball bounces off sideways. The ball, yep, that's this next sentence here. The ball bounces horizontally off the plane at point P1 up here, with the same speed with which it struck the plane, and it strikes the plane again at point 2. So we have some incoming velocity when we hit P1 in the vertical direction that we've picked up. We started at rest, and then we're traveling at some v, and then when we leave P1, that v is completely redirected into the horizontal direction. And then we then accelerate down again until we hit point P2. So we want the speed of the ball just after it first bounces off the plane at P1. That's going to be the same velocity that it has at point P1 as it comes in. So this is the amount it accelerated when it reached point H. So for this, we'll use... So this is technically a kinematic. We used it already. Although you may recognize it from, and if we now plug in, so usually we have this as acceleration times distance, but if we plug in our accelerations and our distances, this is g, this is h. This is starting to look a little bit familiar here. What I can do, I can, and we don't need to do this for this problem, but this is a good way to help get some intuition on where this function comes from. I can divide both sides by 2. And so we have 1/2 Vf squared is equal to 1/2 Vi squared plus GH. Now this might look a little bit more familiar to some people. And to kind of seal the deal here, I'm going to multiply both sides by m. And so I then get 1/2 mvf squared equals 1/2 mvi squared plus mgh. Look at that. This is our conservation of energy. This is a final kinetic energy. Ke final is equal to an initial kinetic energy here plus some potential energy, right? We have some potential energy, some initial velocities, and then we fall down, we travel through that distance to get the final kinetic energy, the energy that was converted from potential to kinetic. That's where this function comes from. However, in this case, we don't need to really deal with it at this level. This kinematic is better optimized for that. This guy here. So let's see. We are starting at rest, so our V initial goes to 0. And we're looking for our V final. So this is almost totally rearranged for it. We just need to take the square root of both sides. So that's going to be the square root of 2gh. Is this symbolic? Yeah, I think this is a symbolic problem. So that means we're not going to be plugging in numbers. We just need to express things in terms of the constants that we've been given, which in this case would be h, l, and 45 degrees. And then we can also use fundamental constants like g. So this means our speed is just going to be v is equal to the square root of 2gh. Oh yeah, look, it even says at the bottom here, in terms of g and h, determine the following quantities. Oh, okay, so I see L is actually one of the things we want to find later. Okay, I didn't read the whole problem ahead of time. That makes sense. So next, we would like to find the time the ball is in flight between points P1 and P2. Okay, let's see. So we are traveling horizontally. We have a horizontal component to our velocity, and we have an increasing x component to our velocity. And so we are traveling an x dimension down this way and an x dimension down this, we're traveling a y dimension down here, an x dimension down here, such that the hypotenuse equals L, but we're going to assume we don't know L yet, right? Because that is what we have to find in part C. But we do know that this is 45 degrees. So that tells us that that y distance is equal to the x distance. And so, and we know our x distance we expect to be covering at, how do we want to do this actually? Let's see. Yeah, and so we expect, we're looking for so the time it takes for us to cover the distance in the y is the same time it takes for us to cover the distance in the x. And so because these are the same thing, we can just write this as our distance in the x we cover is the velocity we have in the x, that's this initial v, because we have that as an initial x component here, times the time. Again, then giving us time, we just divide both sides by v. This is still not in terms of h, but that's okay. Kind of. I would. Okay, well, okay, so let's get an expression for this at least then. And so then that v, we can plug in the v we had, which is going to be the square root of 2gh. Very good. Any questions so far? Looks good. What are we at? 1 minute 10, or 1 hour 10? Again, we're going through these slower than usual just to make sure we've got time to explain. In real life, we probably want to be moving through these slightly quicker. And so we know our x is equal to y. Yeah, x is equal to y from up here. And then the y distance we travel is equal to our acceleration, 1/2 gt squared, plus our initial y velocity, which goes to 0, and our initial y offset, which technically we could write as we are starting at a height y here and trying to get to 0. But if we are looking for this distance y over here, we might as well leave it on this side here. The distance we traversed is just equal to this acceleration term here. It just depends on whether or not we want to put the offset on one side or the other. And I prefer keeping it on this side here. It's just a little bit cleaner. And so, and we know y is equal to x, so we can then plug that in down here. Our time is equal to 1/2 gt squared over root 2gh. And I'm actually gonna, okay, let's actually, we'll go back a step here because we now want to get that velocity back on the same side. I realize now we should probably keep this. I don't know why that's like dancing around. It's kind of fun, but a little annoying. So yeah, when we plug these in here, we can say this is the same thing as equal to y, because our y is equal to our x due to the symmetry in the triangle. Yeah, and we're going to leave the velocity on this side now because we're going to get a t squared term here, right? Y is equal to 1/2 gt squared, which is equal to root 2ght. Now when we cancel the t's, our remaining t shows up on this side. We could have got there from before, but that would have led things to be a little bit more complicated, and then we would have been doing algebra steps just to undo the previous steps we did before. So it makes more sense to just forego doing those steps entirely and rearrange it from here. So now we want to get t on its own on this left side here. So we're going to multiply by 2, and we're going to divide by g. So that gives us t is equal to, we've got the square root of 2gh up here. We want to multiply it by 2. I can't. Can I move these? Do I have a select? I don't. That's unfortunate. On our usual tutoring platform, there's a select key, but that's fine. We'll just multiply the 2 on the edge here, and then we'll divide this by g. Now this can simplify. We have some radical action going on here, so we could combine the square root g with the g, but that's honestly not worth doing because if we do this incorrectly, we lose the points. But for leaving it like this, you can't lose points for not simplifying. Unless the problem specifically asks you to simplify, or it's asking for you to prove something, so you need to get it into the exact form, you will not be docked any points for not simplifying. But you will be docked points if you incorrectly simplify. So it's just not worth the risk. So we're not going to do that. And so now we know our time it takes in terms of g for us to get for the ball to be in the air. Technically, I suppose we should be boxing our answers or circling our answers because last time we were able to fit them kind of near each thing. But if they're going a little bit all over the place like this, then we'll put in little boxes just to make it clear for the grader, right? Although this is Not going to be have an actual grader review this, but I guess I'm reviewing this, right? And so now we want to find the distance L. And so we can use one of these original relationships because now we know our value x here. I probably don't want to circle this. I'll use our laser pointer here. We can use this relation that we got before because now we know the value of t and the value of v. So if we can relate x to L using our trig relations, we can solve for L. And so this angle in here is a 45 degree. X is adjacent to it, although we can actually use the sine relation too because x is equal to y, which is opposite it. I guess sine's a little easier. It doesn't matter because it actually ends up being what's that going to be? 1/2? No, that's going to be root 2, isn't it? So yeah, we've got x over L is equal to either the sine or the cosine. It's your choice. I suppose I'll go with the sine of 45 degrees. That means L, ooh, hang on. Yeah, opposite over hypotenuse. Yep, that's right. Just had to double check I had that the right way around. That leaves L as x over the sine of 45 degrees. And sine of 45 degrees, I should really know off the, we can work it out, right? So for a 45, 45, 90, again, in the actual test, just use your calculator. But we have something to prove here, I suppose. It's going to be opposite over adjacent for either angle. 1 over root 2 is sine of 45. So 1, and that's on the bottom. So this is going to be root 2 times x. Now all we need to do is plug in our value for x. And so x is going to be our v times t. And so we'll still have this root 2 out front times root 2gh. So we'll keep those under the same square root like that. And then that's times t, which is going to be multiplied by, we'll leave this again in this kind of format. This definitely could simplify, but we don't have to. So we're going to leave our L like this. This is in terms of G's and H's. We could see that this this root 2gh shows up here, so two roots multiplying each other gives the undoes the square root if it's the same thing. We have a root 2 kind of coming in here. Okay, yeah, fine. Well, let's simplify this because this is it's gonna annoy me otherwise. It's my curse. What can I tell you? So we have 2 root 2 out front here. And then we have a 2gh, so I suppose that would be 2 times 2 would be a 4. We'll replace that as a 4 times root 2 gh. We have a g on the bottom. The g is going to cancel, so we'll just have it be like that. Our L is 4 root 2 h. I am pretty confident I did that correctly. So we have the 2's, yep, the root 2's cancel. We keep that one root 2 there. That looks good. Yeah, okay. Again, I would not recommend doing that though, because if you were to make a mistake doing that, you lose those points, and that's just not worth it. D now asks us to find the speed of the ball just before it strikes the plane at P2. We might need a new page, honestly, because we're kind of out of space. Let me get us a fresh page here. Here we go. I'm gonna add in the original thing here, the original problem. Where's my mouse? Okay, I guess I'm using the thing here. That's fine. Nope, my mouse is gone. Come on. Oh, it's down there. That's not very wise, is it? Goodness me, why did I do this? Okay, go. I can't get the picture in, and now it's in the wrong window. Okay, if I Alt F4, that's going to exit everything, isn't it? Where's my mouse? Okay, there it is. Yeah, I suppose the fact that this is on stream right now means that I'm unable to like use the dialog box that this is looking for. Oh, but I kind of work this. There we go. Okay, I can now see my mouse. Kind of. Not really. I can make this work though. So let's see, that was AP Physics. What FRQ was that? That was the bouncing ball one. That's God, why are the thumbnails so tiny? It makes me feel old. My eyes don't work as like they used to. There we go. Okay, that was what we would call needlessly complicated. Okay, so sorry, I guess next time I won't try to pull up the thing each time. But now that we got that all set up, so we are looking to fill out part D here. We got the previous stuff, L and T. Now D is going to be the speed of the ball. And so we want to think of this as a triangle again. We have our total speed as we hit P2 is going to be in this direction. We have our net velocity. We have a y component, and we have an x component. Now the x component is unchanged. The x component is the same x component we had coming out of P1, which we had from before. That was, I will double check, but let's see. That was root 2gh. There's a very anxious little dog outside. He probably just saw someone walk by the window, and he's a nervous creature because he's about maybe 15 pounds. Oh, nope. That's what that was all about. Okay. So now we just need to find our velocity in the y direction. Now we can do this using, I mean, I guess our best bet is just to use our relating our velocity to our distance formula. We started at point P1 with no downwards velocity, right? This was all moving in the horizontal direction. So our VI squared goes to 0. And then we have this as 2AD. But our distance is the y distance, which is the same as our x distance, which we had as VT. So that's this answer without the root 2. So that's 2h. No, it's not. Yeah, no, hang on, it is. Sorry. It is this, sorry. So x is L divided by root 2 from this relation here. So we can just take out this root 2. It's going to be 4h. So it's going to be useful that we simplified. Our acceleration is still g, and our distance we just said is 4h. So Vf we get as the square root. We'll combine that 2 and 4 to give us 8gh. And let's leave it like that for now. This is going to be in the y direction. And so this also simplifies again. We can pull out a radical. This is square root of 4 times the square root of 2, and square root of 4 is just a positive 2, so we can pull out a positive 2. But we're going to leave that for now because we want our net velocity. We want our speed in both the x and the y. And so we've got to add these in quadrature, or another way of thinking about this is we're just finding the hypotenuse here. So that's going to be the Pythagorean theorem. Our velocity is equal to, well, so we expect v squared to equal vx squared plus vy squared. That's Pythagorean theorem, a squared plus b squared equals c squared. In this case, though, we want the square root of both sides, so that's going to be the square root of both of these squared. And so when we square these, on the inside, this takes out the square roots, and then we can add them together, and then we take the square root again. So we see our v is going to equal the square root of 2gh plus 8gh, which we can leave like that if we want. This is an answer in terms of g's and h's, but we can do this a little bit better here. That's equal to the square root of 10gh. And I think I'll leave it at that. We'll make a nice little thing right by the answer, just so we make sure it's clear. But yes, this is going to be our answer for this one. Our speed reaches the square root of 10gh. Cool. Any questions so far? Looks pretty good. Cool. And so I think this is our last problem. And so this is now going to be an experimental design type of problem. This is going to be one of the types of FRQs. I don't think this is on the digital exam, but this will be on the written exam. And so what you have to do here is you'll be asked a hypothetical, and you would design an experiment or an experimental method for how you would go about finding the values they're looking for. So let's take a look at what this means in context here. So we've got a world-class runner who can complete a 100-meter dash in 10 seconds. That's pretty fast. Past studies have shown that runners in a such race accelerate uniformly for some time t, and then they run at a constant speed for the remainder of the race. So we've got constant acceleration and then uniform. So acceleration then drops to 0 once they've reached that maximum speed. A world-class runner is visiting your physics class. You are to develop a procedure that will allow you to determine the uniform acceleration A and an approximate value for t. So that's going to be the time they travel at that uniform acceleration before they reach that constant speed. By necessity, your experiment will be done on a straight track and include your whole class of 11 students. Okay. I don't know if the 11 is relevant there, but that's nice to know. We have extra students to help out. Oh, I suppose that's actually, yeah, no, that's probably to compare multiple different runners. So we need to, so our first step is to choose what we want to, what items we want here. But before we look at A, before we do A, let's take a look at what B is going to ask us. B is going to then outline the procedure that we want to do. Oh, excuse me. Encore? Oh. I feel like there's a second sneeze coming, but it's not coming anymore. So we're just going to let it go, and it's going to catch me off guard as soon as I start speaking. So B asks us to outline the procedure that we would use to determine A and T. So we want to think about using the items that we would choose here. How would we set up our experiment, and what would our procedure look like here? So we might not be measuring acceleration directly. In fact, we kind of can't measure acceleration directly. But it looks like we've got objects to measure distances, measure time. There's a starter's pistol, so we can have everyone start at the same time. Or if you get really angry at one of your classmates, no, that's don't do that. And so we have to discuss how each of the items we chose in part A would be used in part B. And then C asks us about the analysis portion. So then how would we use the data that we collected to calculate A and T? And so let's see. So we're on a running track here. We're looking to solve for an acceleration. And we know acceleration is, so that's going to be our change in velocity over time. And we can think of our velocity as being our change in distance over time, our change in position over time, which is distance over time, but I suppose let's actually be a little bit more specific about this here. Let's call this x final minus x initial. So time is easy to measure. That's going to be with a stopwatch. So we'll take a stopwatch. And we can use different x positions. So this is going to end up looking sort of similar to those car problems we saw in the multiple choice section. So I'm envisioning a sort of track here. And we've got, let's say we're running left to right. and we've got our runners at the end here. I guess I'll just draw the one, but we'll have all 11, well, all 12, because we've got 11 students plus, maybe we'll have some students help. You know, we have whoever's running will run, start at this end, traveling this way. Let's also take some chalk and tape measures. And so what this will let us do then is we can take various intervals along the track here. And so as we measure increments along the track, we can track their velocity. So we will then measure the time at each step. And so we can see as the time gets smaller, what the change in the distance would remain constant because we measured out each distance. And so I'm speaking out a lot of these, but these should be things you would write down in the thing. I'm not gonna, my handwriting's not great, so we're not gonna do too much writing here. But so we would have measured the constant distances. We'll write these as delta x's because we want little changes between each little interval, like that, right? And then we're collecting the time each time we pass one of these chalks. So I guess we would say marked with chalk, just so we can justify why we took the chalk. Technically, we could do this without, but I mean, like we could do this with like meter sticks, and we just put a bunch of meter sticks and count where they go by. I think the chalk would be easier. I guess masking tape is another option. We could put that on the ground, or use string. Maybe you have a rope. I guess we'll probably want a starter's pistol just to start us off. We don't really need it. We could just have the stopwatch and tell them go. I mean, it's less firearms in school, which is probably a wise decision, but you know. So we want to measure time intervals between our constant x's. So yeah, our constant changes in x. And so this will tell us then, we'd get some sort of table. And so now we're moving into a little bit of part C along with part B now. And so C would tell us, we'd have a set of x's. And so if we've got 8, that would be gaps of 12.5. So we'd have, well, I guess we'd have 0, 0. We'd have 12.5, 25, 37.5, 50, 62.5, 75, 87.5, and then 100 meters. And so we would have some times t here. So we would have 0, t1, t2, t3, t4. You know, we'll just go ... I'm sure that would be fine on the AP test as well. They're not going to ask you to be that specific. This is a hypothetical. But we do know we have all these times we measure are for each of these distances. And so the change in time, we expect our change, our velocity to be this change in x over, technically it's our change in time. And so we'll have it be, I guess, yeah, like our relation up here. I suppose we should get this a little bit more specific as our final time minus our initial time. And that's going to be the velocity at that point. And then we would calculate our acceleration by taking these again, but relative to the total time. And so we look for the time, the time t equals when delta v equals 0. So when the velocities start looking constant, So let's write these as when the v's become constant. And then the a would be in that constant, in that region when before the v's become constant. We'll take our average of our times here. So we'll do this in accelerating region. So this is a little bit shorthand here. Realistically, you'd probably want to write maybe a paragraph or so about what this process would be. But what we're doing is we're just measuring distances with respect to time in each frame. And then we can calculate the acceleration backwards from there, from taking our positions with times, giving us instantaneous velocities at each metric. And then in the region, once we know the time t that we accelerate from, we can take our minimum velocity and our maximum velocity, take the difference between them, and divide by the time. In fact, actually, if we're starting at rest, this even goes to 0. So this would just be our maximum velocity. So we want to find the maximum velocity divided by the time that we wanted to get there. And we would get our velocities from our changes in x's like this, and measuring from our stopwatches that we stop as soon as our runner crosses the chalk lines measured out with tape measures. Yeah, cool. And so that's pretty much all we have for our experimental design. We talked about how we would use each of these things we wanted, each of the equipment pieces we would have liked, what procedure we would want to do, and then what our calculation process would look like with that. And so that's actually all I have for us today on kinematics. We took a look at some practice problems, did some practice FRQs. Didn't have as much chat engagement as we were hoping for, so I didn't have any questions to answer on the fly, but that's okay. We're still kind of working things out as we go, you know. As for our next one, we're going to be looking at dynamics. Let me bring this around here. I can actually, let's pull this out of, is that going to screw things up? A little bit. Not too bad, though. Cool. Let's unscrew it up then. Let's get that like that. There we go. That's nicer. So, thank you for coming, everybody. I hope you guys learned something today. I hope you're feeling a little bit more comfortable about your upcoming AP tests. We will be continuing this twice a week until the AP test, which is May 5th. I'll have a look and work out when that digital test is. And so, yeah, next time we'll be picking up with dynamics. It'll be largely the same format as this, kind of looking through practice problems and talking about our process as we go. Well, thank you everybody for coming by. Until the next time, you take care of yourselves, keep safe, and I'll see you all Thursday. Take care now.